Right.
Potential
Talk about
and kinetic.
Potential and kinetic. So that's like stored energy. Kinetic is like moving or using energy. We call that released, I guess, in terms of what we're in.
Or using and moving is kinetic.
And then, what did you guys come up with for the homework one with different
clock.
types of potential
A clock
energy?
wound
Yeah,
up.
winding
So
up clock,
a
a
clock
jack,
is an example
a Jack in the Box
of,
toy.
Potential.
and a jack in the
Clothes.
box is an example. Those are both examples of like mechanical,
Mm-hmm.
where I store it in like a spring.
Spring, right.
Then
there's gravitational, like an elevator.
Yeah, we did that.
Held up.
I worked on a balloon. When you fill it up, it's stored. And then when you release it, it's kinetic.
Huh.
Is the balloon the energy or
That's
or the
elastic,
air?
right? Isn't that elastic because it's being stretched, the balloon itself?
Yeah, no, I think that's that's probably the best way to think about it now.
Elastic energy, so you
that's
knew what I was
like,
thinking.
that's sort of related to the spring. Instead of a metal spring, you're storing it in a rubber spring, kind of an elastic force.
And a bow and arrow was the other one I did.
Bow and
Like
arrow.
when
Yeah,
you
so
draw
that's
the
also
bow
a
part, right?
Uh-huh. That would be gravitational, yeah. And then what was the other one that we talked about at the end? Yeah, so what was that about? It was about, I could also store chemical energy, right? And so then kind of implicit, I guess, in your marshmallow constructions, is the notion that when atoms come together, they can store potential energy, chemical energy, essentially because you have different charges, right? The electrons are negatively charged, the nuclei are positively charged. You get them all in this small region, and so then there's a lot of strong forces because the electrical charges repel or attract each other, basically.
So it's like a battery, a charged battery or something?
Yeah, a chemical energy, those same kind of chemical forces underlie the energy in a battery, and then I think it's Kathleen who brought up the battery on Tuesday. When you then connect the battery, then you're starting to release the energy into an electrical energy where it's moving those charges around.
So when the electricity or whatever it is inside the battery is stored, that would be potential storage.
Yeah, so you actually store it in
In the
chemicals.
battery.
So,
Okay.
like say I have a rechargeable battery, I put the charger on, now I drive actually certain chemicals to react and make other chemicals. So those are like the storing chemicals, if you will. And then when I put the load on, whatever I'm going to use my battery for, then I just go in the other direction in the chemical reaction. So now the storing molecules start breaking up and making the sort of byproduct molecules.
So that would be like with our
if you will.
smartphones. There's a battery, it gets
Right.
stored and all that. I mean,
Yeah.
use it and then we do it again, recharge.
Exactly. So like, and your smartphone probably has like a nickel or a lithium, whatever, nickel hydride battery or something like that, right?
That causes brain cancer, right?
Right, exactly.
If you eat enough of it, I'm sure.
Exactly.
Yeah. Okay.
If you eat enough of them.
So the point being, though, is that for a lot of useful things that we do, we need mechanical energy. I move my arm, my drum, the chalkboard, that kind of stuff. That, for us, comes from basically chemical energy inside our cells. You can think of us as little batteries, big batteries, I guess. And then I argued to you that where almost all of this chemical energy ultimately comes from is from the sun, because plants photosynthesize, and then essentially the whole food chain goes on plants in one way or another, and so that's I don't want to label it as as potential or kinetic per se, but let's just draw an arrow and say it comes from solar energy. And so that's what I wanted to, so solar energy is basically what I wanted to start.
I'm sorry,
Yeah.
chemical comes from solar?
Ultimately, right? So here, let's do a more detailed kind of bit of logic. Not, well, almost all chemical energy, probably you could say, but basically, right, I have solar energy. It goes to the earth, the plants, at least in the case of life,
Right.
take it up, photosynthesis. Then that goes to food, nutrients, whatever you want to call it. So that's the argument. And you could make that argument more or less precise. And you could also do it without, in a less of a living kind of context. You know, certainly the text that I gave you guys a few days ago, you know, it gives the example of like solar heating, for example, if you got water panels on your roof. And it actually, I think, gives, you know, one of these statistics that like the amount of solar energy that falls on the earth in an hour is like the same as the amount of energy the United States uses in a year, basically. It's a huge amount. It's like, in principle, if you could just harvest all the energy of, at 100% efficiency, it's like you could power the whole like U.S. off of like basically solar panels painted on the highway system, which is a tiny fraction of the area. It's hard to move that energy around, which is why we don't do that right now. And it's expensive. So a lot of the energy crisis, if you will, is economic in nature in some sense, that it costs too much to get renewable sources of energy. And by the same token, actually, you kind of say, I didn't want to get into this too much, sometimes be a little bit confusing, but in some sense, right, energy is conserved. We learned that too, I guess I should. So these, their total is conserved. But you could kind of think of energy as being kind of high grade, easy to unlock, or kind of low grade, hard to unlock. Right, so these kind of examples you were giving where, you know, you put it into a spring, it's real easy to basically get that energy back out. You throw the catch on the jack in the box, for example, or, you know, you let the counterweight go, or whatever. Or in the chemical case, you mix these two things together. Other energy is kind of hard to get back. Basically, we dropped the tennis ball on the ground, some of that energy went into the floor, went into the tennis ball. It would be a real pain to get that energy kind of back out. And so a lot of what people talk about with the energy crisis is not so much that there's more or less energy because that the total is conserved. It's that the energy that's really easy to use without, like, you know, going to more work to get that energy out, that's what is hard to come by, basically. So, you know, like, so gasoline, it's a spectacular fuel because its energy density is really high. So you get a lot of energy for a small volume. So then you can truck it around for in a cost efficient way. Whereas, like, you know, they hydrogen fuel cell cars you might have read about exist, but to truck hydrogen around costs more than the hydrogen itself, basically. So that's why people don't want to do it.
I'm sorry, can you repeat what you said about the gasoline fuel? The energy density is
really high. Like, if you make a chart of different fuels as a function of volume, how much energy you get, gas is just way up there. That's why it's a great fuel. Yeah.
It's easy to cart or something.
Mhm. Yeah, so if it's low volume, I can put it in a tanker truck and drive it around.
Doesn't weigh anything.
Well, it does weigh something, but
Wow.
it weighs less per the amount that I get out, the amount of energy I get out. Yeah, by the same reason, token, coal weighs something. It's if you, we drive along the Indiana Coal Road line, you can see those huge coal cars going along, but it's incredibly cheap. So for the difficulty of getting energy out, it's really super cheap, and so then people use it. Okay, so so I wanted to talk about solar though, instead of getting sort of too buried in economic issues. So let me, I think I have enough. Take one of these and pass them around. Each person take one. So what these are they go by different names. They call them, I think they call them on the site where we got them a magic peephole or something. It says it's basically a little prism or grating that's going to separate the white light into colors. I think my wife got these off of Steve Spangler's Science. Have you heard of that? Yeah.
Oh, yeah.
If you haven't, it's real useful actually, just as an aside.
And where do you get all your activity ideas?
Well, so that I put the title of the book on the handout that I gave you. So she's got a whole series.
Oh, it's on the handout?
Yeah, so that's from a book called, so a lot of the ones where it looked like it was all the same kind of pictures and typing and that's from, Janet Van Cleves. It's called like Energy for Every Kid or something.
Oh, yeah.
It's on the handout.
Okay.
And one of them was from her chemistry book. She's got like a whole series. And they're like, it's like $13 a book or something. You get them from Amazon.
Okay.
Yeah, this Steve Spangler.
I actually.
It's like a science
It's
teacher
science teacher.
website.
Yeah, and I actually co-taught a science class a couple weeks ago,
Huh.
and the person that was teaching the class, she got all her materials from.
Yeah, so they have like a ton of
We
kits
did like a
and
rocket.
Mhm.
Oh, we did that.
And we did
Yeah.
like a hovercraft, and some of it is stuff you can use, but some stuff you have to buy.
Yeah.
And we did like a car, a hovercraft. We did a robot. We did
From
a
which
bunch.
website?
This
That
one.
website.
So if you just Google for him,
Steve
this is
Spangler.
like a store. Website.
There's all kinds of cool stuff.
You have to buy all this?
Yeah. I think it's not too expensive. So like these magic peepholes, you got like a whole bunch for a few bucks or something. So does everybody have one? Where did they end up?
Yes.
So here, give me, so I can look.
Rainbow peephole.
Rainbow peephole. So take a look, and over in here, you can look at the lights. Is a good thing to look at, like where the fluorescent lights are. The screen is a little bit disappointing.
Your paper.
Yeah. Check it out.
I've seen double.
That's cool.
So what do you see? You see bands of color, and what order are they in?
Probably rainbow.
Yeah, they're in the order of the rainbow, right? Roy G. Biv, red, orange, yellow,
Yeah.
green, blue, indigo, violet.
That is so cool.
So white light, it actually, right, there is no sort of kind of true white in some sense. It's actually that you have a superposition of all the different colors in the rainbow. You can see that, by other means than, so what this is doing is splitting up the white light, right? Your TV is like red, blue, green, and so when all the pixels are on, then you get like white, right? So there you see a different example of that same basic principle. The thing that I have to just kind of tell you, and then we're going to do an experiment, I guess, to kind of illustrate it, or maybe a demonstration is the right word, is that different colors of light can deliver different amounts of energy. So if I think of light as a wave, then like the red light waves, they're on the low energy end of the visible spectrum. And then like if I go up to the violet end, then that's the high energy end of the visible spectrum. So color, kind of running out of places to write here. So color. What's that?
Did you say it gives off heat or light?
Well, so
Like the red gives off more
so red
energy.
is light,
Right.
right? So
And it gives off
give
more
it
energy
off.
than the violet?
Yeah, so it can deliver more energy to like another object. So in the same way that the rice sack hit the can and delivered energy to it to move it, when light hits you, then it can impart some energy to it, transfer some energy to it. That's why you heat
That's why
up
you
in the
have
sun.
that
We're actually going to go
solar
out in the sun in a couple minutes, basically.
That's fun for the kids.
It's fun for us.
Yeah, so red is sort of the lowest energy. At the risk of confusing things a little bit, you can actually think of light as made up as little packets of energy, and so it's actually how much energy is sort of in each packet. Basically.
Okay.
So colors of the rainbow to violet would be highest energy, and that corresponds, you can think of it more from a wave perspective. So red would be like a longer wavelength, kind of slower, calmer kind of wave, and then violet would be a shorter wavelength, kind of higher, more frenetic kind of energy. And then the thing that you may or may not appreciate is that the visible spectrum is just a teeny part of the electromagnetic spectrum, right? So there's all sorts of electromagnetic radiation that we can't see, right? So up here, well, so right above red in wavelength, what would that be? Do you know? Sometimes you hear about them in the context of like night vision goggles, stuff like that.
Green? No, is it the red, the blue light or the red light or the?
So
That's all inside of the.
that's all here. So red,
Yeah.
orange,
Orange.
yellow, green,
So the night vision
I
is
think
the,
ultraviolet, but I don't know if
is it
that's.
black?
indigo.
Is it black?
Okay, so
No.
Charlotte just said something that's on the other end here. That's ultraviolet. Infrared is what's
Oh,
out
it's
here.
infrared, okay.
And if you kept going, there are other things that
Infrared's
are...
a color.
Yeah, you can't see it unless you have a special
That's crazy.
camera. But right, like if you're you know in the Iraqi desert looking for you know, people planting IEDs or something, then you might want to see that they're giving off infrared, basically.
My son wants
Heat.
infrared.
So the light in a tanning bed is violet, isn't it?
It's
Ultraviolet.
ultraviolet, and that's going to be the key to our exercise, actually.
Causes the most damage because it's the highest energy.
That's right. Yeah, exactly. And yeah, we'll talk about that in a moment. Okay, if I go further up here, actually, there are others, just so you know. So, like microwave your
Yeah,
microwave
stay away from that.
Is what?
That's
is
probably.
lower energy up here actually.
It's a color?
It's a light. It's
It's a light.
a form of electromagnetic radiation.
TV.
Yeah, so TV and radio transmit electromagnetic waves, so they're in the radio frequency basically. So those are even longer. So microwave is tuned to excite water basically. It's at like just the right frequency to get the water going, and because most food has water in it, it heats things up. Radio waves are really long wavelength. That's why actually you can transmit them over really long distances. It's like those wavelengths can be kilometers. Yeah. There are too many familiar things up here. So maybe don't worry so much about here. But yeah, like if I were to cram in a few more up here, it would be like microwave. Radio waves. I guess X-rays should be over here.
That'll be lower.
Smaller wavelength, yeah.
That's why.
Higher.
That's why
They're higher
Higher,
energy
but
and smaller
smaller.
wavelength.
Relative to ultraviolet?
Yep.
Similar?
Yeah.
Okay.
So anyway,
so the lower
you know.
you go, the more, or the higher you go, the more dangerous it is.
No, the lower you go, the more high.
Well, the higher energy.
Yeah, so
Yes.
you're kind of getting to what we're going to go out and do in a moment, which is I have some, I can pass them out while we talk, I have some UV sensitive beads, and so, yeah, actually it's good to do them inside here. So each,
Oh, you go out in the sun and
take one.
Alright.
Yeah, so what you'll see is that in here all the beads look white.
Yes.
And that's because the light in this room is not high energy enough to get them going, basically.
Is this just any white? We could use any white beads for this? No, they have to be ultraviolet.
They have to be ultraviolet
So the whole,
sensitive. I bought them off
They're
here.
like glow in the dark.
Well, they're not glow in the dark, but they're ultraviolet sensitive. They're
So
some
what
particular.
causes glow in the dark then? If we're talking about light, is it storing the light in the
Mhm.
item that's the
That's right.
glow in the dark?
That's right. Exactly. So it's a particular dye that absorbs that energy and then gives it off, basically.
Oh.
And when it's light out, you don't see it so much giving it off, even though it's actually doing it. And then when you turn out the lights, you can just see it better. If you go to the Field Museum right now, actually, they have a bioluminescence exhibit, and they actually have a little display on exactly that question. They have a little plastic dinosaur that glows in the dark.
And they do this activity at the Atwood Planetarium. You go there.
Do they?
So the whole don't stand in front of the microwave or you're gonna, I mean, is that just going above?
That's
and
true,
beyond?
it's still radiation.
Yeah, I don't know how dangerous it is or
Okay.
not. I don't know.
That
Not
means
willing
you
to put it to
still
the
do it.
test.
I mean,
I think anytime
it's like a little
exposure-
overboard, right?
Probably.
Okay.
It's how much
I mean,
you use it.
You are full
That's
of
the
water.
thing.
So, yeah. But yeah, so these beads, they have a dye that requires more energy than the typical visible light can deliver. And so it's only when you get into the ultraviolet where they'll change color. So what you're supposed to see now is that exactly, they're basically white. And then when we go out, the reasons that you were saying with the tanning bed, the sun, it's got energy in the ultraviolet that then can excite those. And by the same token, right, like what do we try to screen out oftentimes? So if you look at sunblock, right, it's like UVA or UVB rated because they actually, all that is that they split the ultraviolet region of the spectrum into two different parts, like a high energy and a low energy part of the ultraviolet.
Oh, so they're both still ultraviolet. I always thought they were two different things.
They're just
Even though they
different
both say
wavelengths.
ultra, but
of
I
light.
thought they were two different wavelengths.
It's like saying blue green and yellow green.
Oh, I see.
It's like
So
slightly
why would you
different
pick-
colors.
Why would you pick one or the other?
Well, probably you want to screen them both
Yeah.
out.
So what,
I
they
think-
sell them like this is only for UVA and this is UVB?
I think they
I
call
think-
it down
I
broad
think,
spectrum is what they call it.
yeah.
They'll put both.
So I think what they're trying to communicate to you is that probably some used to only do UVB,
Right.
and now they're also screening out the UVA, so they're being more cautious is
Okay.
what they're trying to tell you. By the same token, like my glasses, you'll see they're like transition lenses.
Oh, yeah.
So they're in principle, we'll test them. I didn't do it myself actually before. They should screen UV, and I brought some kids' sunglasses too, and we can see if those do or do not actually. I put a question on the handout, which is why is it actually worse to have sunglasses that don't screen UV than to just be out with no sunglasses?
Really?
I would think it's because you're
Probably
because you think
you're
you're not doing
protected and you're
it.
directly looking all over and
Boy, I think.
You're close, you're really close,
Something like
I
Meltita.
think it has.
What
something to
thinks
do-
you're protected?
your eyes.
Your eyes.
Your eyes
Because
have
your
this-
pupils
Yeah, they're
are big
Yeah.
because they think it's dark, but they're actually letting in much more UV than they would normally.
That's what I was thinking. It's like a trick.
Protect your body.
Mhm.
Yeah, so cool, let's go outside. There's some more beads?
Are all these questions?
Upshot of all of that is that different types of electromagnetic radiation, which we normally think of as light, have different amounts of energy. So that kind of completes sort of the energy lecture, if you will. So what I wanted to do for the rest of the time is a topic that is a little bit different, but kind of goes hand in hand with energy for a couple different reasons. One of them is kind of historic and also pedagogical, but not quite pedagogical in the way that you might think of. It's pedagogical more for upper level college age kids. Which is that a lot of the ways that scientists kind of figured out the connections between the macroscopic world that we live in and the microscopic world that you learned about yesterday was through the simplest form of matter, which is gases. The other connection, the connection to energy, is that gases also were the way that people figured out a lot of the rules about what makes something energy easy or hard to unlock. Remember how we were talking about sometimes it's really easy to get the energy out and sometimes it's hard to get the energy out. A lot of there are actually some mathematical rules basically for figuring out what that is and for thinking about efficiency, like the best possible machine of a certain type that you could make and what the limits are, those kind of things. And a lot of those kind of ideas kind of emerge from studies of gases, basically. And so we're basically going to do studies of gases, and I'm going to be up front, which is probably the connection to energy is not going to be like crystal clear, but we'll do some, since it's an important topic anyway. Okay. All right, so first what to say, which is kind of, you might not think of gases as being kind of akin to the kind of materials that we were dealing with on whatever it was, Tuesday. But, you know, so right there, you had the rice sack, you lifted it up, fell down, it hit the can of soup. Those were things you could like feel, right? Air, it's just all around us, right? You know, you don't think of gases as being so forceful. Maybe if you think about it, you say, well, oh, you know, like a tornado, that's like air, which is pretty forceful. It could shave a house.
fan or an air
A
conditioner.
fan. I brought one of my kids' toys. This is called an air Zuka. I don't know if you can
Oh, yeah.
feel it. Can you feel it over there?
Little
Is
bit.
it over there? It's very directional.
Wow.
Yeah.
What is that?
Well,
It's the air.
I'm not a very good shot, unfortunately.
Kind of cool.
Yeah.
What do they do with that? Shoot air?
Yeah. Yeah, so that's all they're supposed to do is shoot air at each other.
Shoot air at each
Oh,
other.
yeah, that moves air a little bit.
Wow.
Yeah, I can
So-
see
That's
it.
totally just moving.
Yeah. Another cool thing. Yeah, so it goes up kind of. I don't know, maybe if I lean down.
Yeah, I can
There you
feel
go.
that. Anyway.
Wow.
Oh!
There, see?
Wow.
That's
It
This looks like a
Yeah.
bucket that can.
Yeah, it's just a kid's toy. It's got this snappy part. Another cool thing, incidentally, it's not part of today's lecture, but if you get some dry ice and put it into water, that makes the the bubble coil cauldron bubble kind of gray kind of steam, for lack of a better word. You can, if you put that in a jar and then have a rubber tube out of the jar into here, you can basically fill it up with dry ice smoke, if you will, and then you can blow humongous smoke rings. If you go to, if you get a chance, actually, it's like the second week of December, the Materials Research Center here does a physics open house. It's called Physics with a Bang, and they do those kind of things. It's really cool, actually. A lot of the demonstrations.
When is it this year?
I think it's always like the second Saturday in December.
Okay.
I can send
I
out
usually get
a
I usually get
reminder
an email about it.
Yeah.
Yeah. So they for that one they have a one of these
that a
industrial
field
garbage
trip that we
cans
take the
that
kids
they've cut the bottom out of
It's
big
for
rubber
Yes, they
and
convert
braid
it
over
into
it.
something like that.
Yeah, except it's much larger. Okay, another example of air exerting force is one that one of you already gave today. Maybe it was Meltita. I think with the elastic energy.
Yeah.
Right? So these are my kids. Hopefully I won't pop it. They're a little old. Right, so like you said, I'm storing energy basically and stretching the balloon, and also I'm actually also in some sense I guess storing energy just by kind of concentrating the air so much.
Okay. Into one place.
Into one place, so that statistically it wants to go into other places. And then, right, I can let it go, and it'll propel the balloon. So I'm getting energy, not so different than a rocket would get
Potential
energy
and-
from burning fuel, right?
You know how a balloon goes always in a, like it just moves around?
Yeah.
Isn't there an experiment where you can make it go straight, and I can't think of
Yeah, my wife was suggesting I do, well, basically the,
how you can make it go pretty much
you can make it go
straight.
on a string. That's what I was
That's
gonna
one thing, but I think there was one where you could just, there was a certain, I couldn't remember what it was. I know I did it as a kid in the classrooms.
I know, and I
You
looked
could
it up
make
on the
balloon
web
shoot
yesterday.
straight by itself, not on a string, and I can't remember what it was.
That one I don't know. But you can do, yeah, like a common thing is to put a string across and a little straw in the string. You take the balloon and then you can actually like attach a little gondola or something, right, to make it look like a tram. Okay, so what I thought we would do is try to actually derive some, by experimentation, some what people call gas laws, basically some rules relating different properties of gases like pressure, volume, the temperature in the room, the amount of gas, those kind of things. And so that's where the handout, that's number 2 on the
Coming up with and strategy.
Yeah, and while we get going on that, I'm gonna set up one because that takes a little bit of time, whereas two of you guys can do mostly, I think, by yourself with a little coaching. Yeah, but so we're gonna, how about we, I think we can do it as a group, and how about we try and do A, basically. I'll try and get you guys started. So what color balloon do you guys like? We have blue and purple and
Yeah,
yellow.
Purple.
Purple.
They're such good ones.
I know.
Do you have tape, Candace?
Want masking tape?
Any tape. Visualization, and it makes the point
Yeah,
that
I just thought
somebody,
there were numbers
and they know who,
Oh,
like
okay.
in a particular paper, invented the bar graph.
Oh, really?
Like you think to yourself, oh, that's like,
Like
prehistoric or something,
Yeah.
right? But no, this one guy who was like a shipper in England invented the bar graph, the pie chart, and
Wow.
one other
Mind graph?
graph.
Histogram?
I like teaching graph,
And,
like
I love
It's
graphing.
fun.
I love teaching
one
them
paper.
graphing on Excel too.
Alright, what do you got? Oh, you got 0.1 for everything.
No.
That's not
That's
good.
a question.
I know, why? But, look though,
Because your balance isn't
but
so
we
accurate.
we measured every balloon. So should we not have done that?
No.
Yeah, you should.
Okay.
Because
We
they
need a
have
lift belt.
So,
So
what was
let's
the
see.
balloons, on what part was the balloon in the tape? Was it these or these?
The first one is the initial weight
Of the balloon.
of the balloon
So this is the-
without air,
So
and the tape.
this is balloon
And
tape
tape.
plus tape.
no air.
So,
This is the balloons with
With
air.
air. Balloon
Plus
and
tape.
tape with air.
so you
So,
had
yeah.
one at 0.3 and 900. I guess I should have drawn my scale here.
And then one's
We'll bend good behavior. And then we had one at 200, one at 500, one at 700. Wow.
Is this the second one?
So, yeah.
Well, I'm wrong. I'm switching mine around, see?
Yeah, so your resolution is kind of too low here. You should have, these should have fallen
It should be
somewhere
linear.
in here, basically.
If we had that digital scale.
Exactly, you could easily go out. I'm kind of surprised actually because, like I said, when I blew up a balloon yesterday and stuck it on my kitchen scale, which is a digital scale, but it goes in
Should've
2
brought
gram increments. Well, so it's actually less accurate than that in principle.
But
And
what's
it
the
claimed
technical
it was
reading?
like 4 grams, but yeah. Maybe that's mostly the balloon. Yeah, so what should you have gotten?
She must remember we should have put more air in the balloons.
Yeah, one could try
To have
and,
a
right
pump up the range,
Well, we couldn't make it
basically.
too high because the.
Except the problem is that then it's hard to get
Beaker.
the volume.
Oh, we had a bigger beaker.
I mean, if you want, we can guesstimate it.
We could have
except that
made
it's
a couple
actually,
much smaller.
it's really hard to see a volume difference. So let's just talk about it a little bit, and then we'll do a different one, which.
Is there any reason why this shouldn't have been a linear?
Yeah, so it's supposed to be linear. I don't know if that's a priori obvious among all the possible relations that you could have, but indeed, actually, a gas, if you double the amount of the gas, which means doubling the mass, then will double the volume. So you would expect something like, this, let's say, for sake of argument. Yeah, okay, so the...
See, this is what's tough when you're teaching science is when you do have errors like that because maybe the scale isn't accurate. So what are the kids really grasping from it, you know?
Yeah,
They don't
so,
actually see.
exactly. So if I were a better person, then I would have pre-run it to make sure that you had, enough resolution. Which, yeah, you would want to do, I think, if you were dealing
With kids, with their, yeah.
Yeah. Yeah. It would also be, in some sense, your classroom, so you had a little more latitude to monkey with these things before.
Right, especially before an observation.
Yeah. Exactly. So, okay, so what have we learned now? We did the cans there. The whole idea is that gases can exert force, right? And that if we, there's another thing actually you can learn from that demonstration, which is the whole point of having the water, right, is that it becomes steam. It's doing some of the pressing out on the can. You cool it down. That steam then recondenses to become water again. And the water doesn't push much on the can sides. Why is that?
The water doesn't push much, you said?
Wait, what was the question? You said-
Okay, we can't fill this.
So when I condense the water, when I condense the steam, it becomes water again. And so what I'm really asking is basically what's one of the fundamental differences between a liquid and a
The
gas?
gas takes up a big volume and the water takes up a much.
Exactly what Bridget just said, which is that a gas takes up a tremendous amount of volume for very few atoms. Whereas a liquid, they're basically packed in there almost at the density of a solid. They're not as regularly lined up, but they're really, the atoms are right up against each other. And so it takes much less volume.
Why is ice?
You say you have become a crystal.
Is it filled with air inside it?
You become a crystal. You have a structure.
When you said, which one takes?
Okay, this one I can actually answer if you guys like it. So it's a very special crystal though. Most crystals, if you the solid, the crystal would be less volume than the liquid. Water is an incredibly special liquid is the answer, which is, and I don't know if you did this yesterday, but the structure of water is like two hydrogens here, and then there are actually two electron pairs sticking out over here, okay? And I don't do it justice drawing it here on the board. If I had some marshmallows like you guys did yesterday, then it's a tetrahedron, okay? So if you want to demonstrate this for your kids sometime, then it's legs back and forward, and then arms this way. So here are my electron pairs out on the fingers. Here are my hydrogen atoms on the toes. So I have this tetrahedral structure. That's also called a diamond structure because diamond has that structure, the carbon atoms in diamond. And then what happens is that these hydrogens are a little bit positively charged, and the oxygen is kind of a little bit negatively charged, so they attract each other. So then you get other hydrogen molecules coming and forming kind of a real nice interaction. And with the particular lattice, which again has this kind of diamond-like structure, is kind of more spaced, a teeny bit more spaced out than if the other water molecules were not quite as nicely arranged and kind of higgledy-piggledy around here, basically. Yeah, that's incredibly important for a number of reasons. One is that in the wintertime around here, where is the ice on a lake? Is it on the top or the bottom?
Top.
It's on the top because ice is less dense than cold water, and so fish get to continue living underneath instead of getting crushed by the ice. There's another incredibly important consequence of the fact that ice is less dense than water. I don't know if any of you know what it is. It pertains to the midway down here, actually.
But hockey,
The ice rink
The ice
is
rink,
down
yeah.
there. So the reason you can skate, you can ice skate, is that the pressure from your skate pushes down on the ice, and actually in order for it to respond to that increased pressure, it turns back to water because water is denser than ice, and that water lubricates your skate. So you couldn't skate on whatever, carbon dioxide.
Let me ask you something.
Yeah.
I am remembering something about the angle of the two hydrogen.
Yeah, so that's all part of this sort of diamond structure, basically. So if I do, light thing here,
Yes.
then the angles between my bonds, so to speak, are 109.
Okay, and then the angle between the two hydrogens is what, 67 or something?
This angle?
Yeah.
It's close to 109.
Okay, I will look.
Yeah. So it's close to a perfect fit. Okay. All right. All right, so I got another exercise. We'll hope it works better than this one. And then also something to kind of illustrate. So how would you guys come around to the other side here? I'm going to come around this way.
Yeah, one to the right should be books, maybe. And volume on the vertical axis.
Remember to,
So let's use, let's use two. Actually, we can use one.
I'll do it.
Right.
You want me to use,
Put some
One
clarification.
and twos. Maybe
Oh.
twos, probably twos.
Actually, we should do it the other way.
You want it up here?
No. But this axis we should call pressure, because that's the thing that we
Pressure line.
think it is, and then we're measuring it in number of volts.
Okay.
That's our unit.
Oh,
This is milliliters.
Are we gonna be returning the sand to you today?
I can turn it on Monday.
are we gonna see you on Monday?
We're not gonna see you on Monday though.
No, I give it to Candace.
Okay.
Turn in what? This?
What we're doing right now?
The question.
Yeah.
You're turning today.
Yeah, I think you can answer one, and then this is 2B. I think we can do that.
Oh, 3, I see, okay.
We have a little bit of computer monkeying. One more, right?
Mm-hmm.
Yeah, pretty good.
Nice, John.
Okay. So, to paraphrase Charlotte, is it linear?
No.
No, it's not really going up, so,
It's curving.
I could have a linear thing go down.
Okay,
Yes.
that's true.
but it would look like a nice straight line if it were
Right, it's
linear.
more curved.
Whereas this thing, yeah, exactly, like Peter just said, this thing is definitely curved. So, the good news is it's supposed to be curving. And that kind of makes sense, I think, from your intuitive kind of sense about gases, I think. Like if I squeeze on something, it gets harder and harder to squeeze, basically, right? At some point, it's pushing back so much that I can't squeeze it anymore. So it's got to flatten out, basically, even though it seemed easy at first, right? You know, you can see that if you take one of these syringes and you just stick your hand over one side. Then it's real easy that first little bit, it's real cushiony. And then as I go harder and harder and harder, oh, it's really hard to push, right? So what does that mean? Well, what it means is that basically you get to eliminate one relationship, right? So if we want to do it in the language of the scientific method, since that's what Joe told me I'm supposed to do, then, right, if you were to say my hypothesis is that volume varies in a linear fashion with pressure, then you would say I just rejected that hypothesis, right?
This looks like exponential.
Yeah, so okay, so now what Charlotte just said, I don't know if everybody heard, she said it looks like exponential decay. I'll actually tell you a secret, which is not. But what you're getting at is, well, okay, what do you do now? Once it's not a straight line, then what do? Do you just pack it in or not? No, you want to try and figure it out. So there's basically two ways, I guess you could say, that you could do it. So the way that we're basically going to do it, which is a perfectly respectable way, used in many cutting-edge scientific papers today, is that you guess, which is to say you form a hypothesis for other functional forms, you calculate that alternative functional form, and then you ask, did that one give me a straight line? In that case, well, maybe I should. Let's do that one first. So Charlotte just guessed. She guessed exponential, right? Or she actually guessed minus exponential. So her thing, like, okay, so when the first one, if we were to try to write that in math, so to speak, the first one we eliminated would be like V equals some constant times the pressure, where this constant could be a negative conceivably, and that would be like a straight line, okay? So this is the one that we just basically eliminated.
Okay.
Then Charlotte's guess was V equals to K e to the minus P, and then I'd actually, I'd probably have another constant in here to kind of deal with my units, and I'd call that P naught or something like that. So, one could, in principle, try that. What you would do is you would take your P's, right? You would plug them into e to the minus P, and then you compare it against the V's and see if you've got a straight line then. Because if I think of this whole thing as some new variable,
Yeah, then I would get a straight line going down.
I don't know what you want to call it. Let's call it U. Then I would expect U and V to vary linearly, right?
Okay.
I'm going to tell you it's not exponential because otherwise we'll be here all day. Okay. Anybody want to guess another functional form that seems consistent with the fact that it's getting smaller as the volume is getting smaller as pressure is getting larger? No, logarithm varies, is increasing with the
Then it's
argument.
the inversion one, okay. So this looks like it happened in the round.
So you're thinking polynomial, it's kind of getting warmer.
I don't get what we're trying to find right now.
An equation
To
for
see
the
if
graph.
it's,
We want to
if it's
find
exponential,
what is our
polynomial,
relationship
it's
between
not
V
linear.
and P. It's not linear,
It's
right?
not
That would have
exponential,
given
that's what you
me,
just said.
that would have
She was
given me
thinking
like a
So we
straight
want like a
line
linear
like that.
equation. No.
Or a straight line like that. Charlie guessed it's exponential, which is not a bad guess the way the curve looks. It's actually on the sheet that
Oh.
I gave you, which is, let's try V equals to some constant divided by.
Sheets.
I don't see it anywhere.
Here.
Mass volume, temperature, and pressure.
No, here.
Yeah. Try
Just
plotting.
Try
whatever.
plotting one volume instead.
Yeah, and so I actually gave it to you the other way. So here I got it as volume equals something going linearly with 1 over pressure, right? But what could I do? I could multiply by P and divide by V. So I bring this one up and this one down, right? So I could also have equivalently P equals K over V. Yeah? So let's try it, huh? Let's see, you guys put, which one do you want to do? We could try either one.
Oh.
They're the same.
He's giving it a data point.
4 and 9.
Let's do 1 over V. So there, what I need, can I take away this?
Sure.
Everybody got this? I need to make a new column.
The inverse of V.
Which is going to be 1 over volume. And then you got to do a little bit of a calculator function in order to.
Okay, what do you want? The
So.
inverse of the volumes?
Yep.
Okay.
1 over,
Right, so what are we trying to do here in the bigger scheme of things? Which is kind of what Kathleen was saying the other day, which is you want to think about how to use a graph to basically learn something. If every time you plotted a graph, it told you it was linear, you wouldn't have to write the graph, right? So here, we're looking at something where we actually have to do a little bit more work to actually find what's the relationship. Yeah, people are with me?
Mhm.
Yeah, so yeah, sure. What's 22, what's 1 over 22.5?
0.044.
0.044, you said? Okay, 1 over 18.
1 over. We're dividing. Quick. 0.05. Repeating.
1 over 14.
0.0714.
Point 09.
9 what?
Point 09.
Repeating.
Yeah.
0.091.
Go up, I'm rounding.
Oh.
1 over 9.
0.1. Repeating.
1 over 7.
0.1428. Or 29. Yeah.
1
Is
over
that a
6.
3?
Yeah.
That is. 0.1.
Hold on, I have to make it look pretty for Kathy.
No, she said 1.148, not 3.
Yeah, I know, he rounded it. 0.16
Oh.
repeating.
5 is gonna be 0.2.
So. Okay, that's a 4.9, that's almost 0.2 again.
That's a 0.2 to 4. 4 is gonna be 0.25.
That's true.
3.2.
4.3. Okay, should we give that one a go? Okay, so let me just pick
Wait,
a
you
couple.
have too many.
No, did you do 0? Did you do the 22.5?
Yeah, 0 is 0.44, 1 is 0.55, right?
Point
2 is,
zero.
No. I mean, it's not the most beautiful
I think we have-
lineup.
got
1, 2, 3, 4, 5, 6.
Oh, good.
7, 8, 9, 10, 11, 12,
oh, 5, 6 is 1.
Okay, tell you what, to make this clearer.
7
This
is
5 is
20. I messed up.
clear.
Okay,
Yeah.
so, oh, I guess I will. So, 1, 2, 3, 4, 5. So this will be 0.03, 0.06, 0.9, 0.2, 8, 0.21, 0.24, 0.27, 0.30. Okie dokie. You guys with me? You're doing it yourselves? Good.
Mhm.
Alright, so.
Alright. Their data. 0 and 1, 0, 4, 4.
This is okay.
So you should have the same line if it's the equation for it, right?
No.
Oh.
Oh, shoot, crap, 0.
Yeah, tonight is just cheating.
So you can't put
Okay.
the 0 on the y-intercept?
I can put it wherever I want, sure.
No, I was just wondering, like, for future, like, when you do it with your kids.
You know, I think
Is
it's,
it better to show it the way you're doing? Because normally,
I think it's probably better to stick it over here.
Zero, zero.
Zero.
I mean,
On
there's
the
nothing
y
that says you
intersect.
couldn't have a graph that went over to negative numbers, right?
Mhm.
I mean, this is basically -1 here. It's probably, since you know that
oh,
the
okay, I see what you're
the
saying.
pressure is a positive number, it's probably more natural to start it at 0.
Okay. This is a tiny bit better, except those two shouldn't be so.
Oh, that's okay. You know, it's a real experiment then. Uh, 0.31. I think it's pretty good.
Yeah, really good.
Yeah, and you know, I think that one probably you could do even better actually if you weren't fiddling around with too large textbooks
Yeah.
and that kind of thing. Yeah, so, but I think it is actually, you know, kind of cute to use the textbooks. Like it can be good, like if you've got kids like to do it down on the floor, you know, and then kind of, you know, they're standing on either side, somebody's down, or, you know, that kind of. Yeah, so that's cool.
Novels
So
and
the
smaller, like library books.
right, so yeah, so you know, you could have conceivably have guessed other things too. Like if you might have said to yourself, well, I think it's going well. So Charlotte guessed that it was going down faster, basically, than this. You might have said, oh, I think it's going down faster, but not quite so fast. So you know, you could have imagined trying like, you know, p over kv squared or something. You know, or you could have had some constant here, stuff like that. So you know, what it comes down to, the reason that people are often successful guessing is that certain forms are recurrent. This is an inverse proportionality, you would say. And so oftentimes the first few guesses work, basically. How many of you were math teachers? Charlotte, a bunch of you actually. So let me tell you the other way you could do it. If you didn't want to guess and leave it to chance, so to speak. If you get it, great, and if you don't get it, because it's a little math oriented, then it's not part of the course. Okay, so what you could do, I need somewhere to write.
If anybody saw that, I think it would.
Really? You guys got it?
Copied, I think, right?
Yeah. Does everyone finish copying?
I can leave the data up, but I'll take away this and you guys can draw your own graphs. So kind of as we highlighted just over here, like I was just saying, there's only so many different relations that you might imagine, basically. You might pick an exponential or a log, but if you're not going to pick an exponential or a log, almost always you're going to pick a polynomial or a power. So let's just suppose that I had something, some quantity, whatever it was, that varied as x to some power. Let's call our power a. Okay. So I want to. So what we basically did is we just guessed that a was -1, and we figured it out. Basically, that we got the straight line. Basically, right? What if I didn't want to guess? What if I thought, oh, maybe a is going to be some crazy number like 0.7 or something. How would I ever find that? I'd be guessing all day, right? You wouldn't want to do that. So there's a systematic way to find a too. And that's to take the log of both these sides. Okay, so if I take log y equals log XA, okay? Then, anybody remember the rules of logarithms? What happens to this, what can I do with this A if it's up here in the argument? It can come down to here, right?
8 times log of x.
So this becomes log of y equals A times the log of x. And so then, actually I'm home free. I can see that this could be like a new variable. Let's call it, I don't know what you want to call it, u. Okay. And then this log y could be a new variable. Let's call it v. And then what have I got? I've got v equals to a times u, a line. Where I can read off a from the line as the, what? The slope of the line, right? So then, what I do
That's why
is
it goes
when I'm confronted with data that I had no clue, like what I should guess, then a very common thing that people will do they'll plot the log of x on one, the log of y on the other. If they get a straight line, they immediately know that it's a power law relationship. And then they can just calculate the slope from that and read off what that power is. So if you had done that for these data, plotted a log of number of textbooks versus log of volume, you would have gotten a straight line with a slope of -1. So if you got that, because you're used to the rules of logs from math, then great. If you didn't, then you can go through life without that little trick.
no matter what kind of horns I put on, I cannot make my students think in logs. Okay.
Well, you know, back in the days before digital calculators cost pennies, right? Everybody used a slide rule.
Yes.
And how did you multiply on a slide rule? You added logarithms, right? So that's what's basically going on here. It's just the multiplication rule, basically, right?
They're convinced that I was around when the dinosaurs were because I know what a slide rule is.
Okay, tell you what. Okay, so good. I wanted to show you one thing on the computer just to kind of illustrate what's going on. But so what have we done? We have convinced ourselves that gases exert forces. We did an unsuccessful experiment to show that to show that as we increase the amount of a gas, the mass, we increase the volume in proportion linearly. We did a successful experiment to show that as we increase the pressure, we decrease the volume inverse proportionally. So linear with 1 over v. I was going to try and show you, but it's not, temperature difference isn't enough. How do you think that the volume changes with temperature? So if I make the temperature higher, will the volume of a balloon get bigger or smaller?
Oh, well,
Bigger.
Bigger.
It gets bigger, right?
Yeah, I put a balloon in the dry ice over there, but you can barely see the volume change. I can pull it out. You can see, but you use the liquid nitrogen is to basically pour it on the balloon. Then it all spills off. It's safe. Air is mostly nitrogen. You don't want to freezer burn yourself, basically. And then maybe a little bit bigger. What do you think?
I think I
I thought you said
Saw
it
it
was
expanding.
hot.
It should be expanding right now. It's warming up a bit. That one's just
No.
dry ice,
Oh, yeah.
so it's not as cold. And so you can play games like that. So let me ask a different question, and it's related to these kind of things. what about, let's hold the volume constant. So don't picture a balloon now, picture like a nice canister, for example. How would the pressure change as I increase the temperature? Do you think the gas would be pushing
It
harder
would push harder.
or pushing
No.
or
Push
less?
harder.
If it were getting warmer,
Yeah.
No, I think if it's colder, it gets higher. Think about if you were to put a can in the
is it
freezer, it explodes. Like,
Yeah, that's true.
A
Is
can
that a
filled,
gas?
that's a liquid.
That's a liquid. That relates to Bridget's question about ice.
because I was thinking I had.
Right, so the reason that the bottle breaks when you put it in the freezer is that water is this very special liquid that expands when it freezes, so it does get a little bit bigger and it breaks the bottle. The gas, actually, the pressure, well, it increases with temperature, so when you make it hotter, it's pushing more, it's really going at it. And when you make it colder, it's pushing less. So let me see if I can get my computer to
Right. With
on the internet. It's amazing, actually. Like, I don't know what people do with their time, or how they have the time to put all these things up. This, I guess, is from Oklahoma State. Again, I guess it's actually from a teaching exercise. But yeah, anyway, well, I should wait.
Is it going to move things itself?
I didn't go through it much myself, I confess, but there is actually a little bit, a handout that suggests ways to explore. Everybody back?
Yes.
Okay, so what I wanted to do to kind of end was give you some sense of what's going on at the microscopic level with gases, right? The whole way we got started was by with gases was by saying that they were sort of the way that scientists through the 18th and 19th centuries basically learned about the microscopic world. So it was actually kind of because of gases that they realized that there's atoms in the first place, and then some rules about how those atoms interacted and stuff like that. So what this is I just found it on the web. It's a little probably Java applet where they're simulating the motion of some gas molecules, and then what you can do is play around with different settings to kind of get a sense about where the different microscopic behaviors come. So what they're doing here, I guess, is setting pressure as the output, so to speak. So I have my hands on some things, and then some things get to respond, right? So I put my balloon in the cold, I'm setting the temperature, and I'm letting the volume do what it wants. For example, and the atmospheric pressure is also set. Here they're saying, what pressure would you come in? So that would be like the last thing that we were just talking about. What happens if I change the temperature? What happens to the pressure as I change the temperature? So you can mess with different things here. So if I go over here, I don't stand too much in front of everything. Let's see, can I move it? This way. Is I can mess with the volume, for example, and I can make this a little bit bigger, and then you see that the pressure goes down, right? And if you were to perform a computer experiment analogous to what we did with the syringe, assuming they programmed it right, then you would see the same relationship that we found over there on the board. Or I could squeeze them down, and then the pressure really cranks up, for example.
Wait. Pressure gets higher when the volume goes down.
Yeah, and that's what you discovered, right?
Oh, that's what you said, right.
If you make the V smaller here, this side is going to get bigger, because I'm dividing by a smaller number, and the pressure is going to get higher.
Gotcha.
I think I can swap it around, right? So what we did in our experiment is we actually varied pressure right? And then we asked what was the volume. So if I start cranking up the pressure, it starts squeezing down the volume. And it's really doing exactly what we did in the syringe case, right? By the same token, I can mess with the number of molecules. So that's like when you change the mass, right? Well, let's do it with this one. So if I increase the number of molecules, you can see that it starts for the same amount of pressure, it makes a bigger volume. It pushes harder to push out on the piston. Why is that? If I got twice as many guys that are pushing, right, there's twice as much opportunity to give it a shove up there. And then by the same token, if I make the temperature higher, I'll also make the volume bigger because now they kind of got more energy to impart to the wall when they slam into it, basically. So
You increase the temp and it increased the what?
here it increased the volume. It's a little bit more intuitive maybe if I swap it back to the pressure. So there, if I increase the temperature, or if I decrease the temperature, then I'll decrease the pressure. And that really is basically the rice sack and the can experiment. The amount of energy that I put into there, it's kinetic energy in those gas molecules. The amount of energy that I put in those gas molecules is going to be related to how much energy they can impart to the wall, basically. Incidentally, just as a little side note here, what they're plotting over here is a histogram of the speeds of the atoms or the molecules in the gas. So a higher bar means there's more molecules with that particular speed. And so what you're supposed to see there is, first off, that not all the molecules in the gas are moving with the same speed. Some are really fast, some are slow, some have some average speed. When I teach general chemistry, this is where we go over the difference between the mean and the mode and the median, if you guys do that in math class.
Oh, yeah.
If I crank up the temperature a little bit, then what happens to the speeds? They go up, right, on average. So I'm higher kinetic and higher temperature corresponds to higher kinetic energy in the gas. The speed is increasing. Yeah, Bridget.
What did you say about the increase of the temperature and the pressure? I heard you say increase the temperature, it increases the volume. Did you say that?
So if I remember, I always got to hold some things constant. So if I hold the pressure constant and I increase the temperature, I will increase the volume. On the other hand, if I hold the volume constant and I increase the temperature, I'll increase the pressure. There's one combination law that actually contains them all. It's called the ideal gas law. I don't know if you guys ever heard of it.
Yeah, 50 years ago.
Yeah, I mean, it's kind of beyond the course, should we say, but it turns out that pressure times volume equals the amount of the gas. Well, here, let's do it this way. Divided by the amount of the gas times temperature equals some constant, which we call the ideal gas constant. For current, so what that says is that I can fix any three of these and read off the fourth one, basically. So that's why it can get a little bit confusing, because I gotta know which ones I'm holding on to and which ones the free variable.
Question for you.
Yeah.
We're looking at helium right now. Would xenon acting differently?
It would be heavier. See, so there you draw them bigger. that's something we didn't get into too much when you guys were doing the experiment. So I kind of used mass and amount as interchangeable. The n in that relation that I just wrote is actually the number of molecules. And so I would have different masses for a heavier gas versus a lighter gas. So helium is like a really light gas. Neon is still a pretty light gas, but heavier than helium. And so what I would actually want to do is convert to how many molecules are there. So, and there's, that
Okay.
going between masses and numbers of molecules is straightforward, but not
No,
something
I
we're
know
going to
how
do
to do
today.
that. Okay, another question, and this is absolutely, maybe I should look for this for later. I want to know, my husband thinks he's told me, but I don't think he has. If you have a star and it starts grabbing energy, like you start making, first you make helium, and then you make hydrogen, and you make this, and you make that, and then when you make iron, the whole thing is finished. And I still don't understand why that is, and I can easily be told to be quiet and ask somebody else if you like.
You don't have to be quiet, but I don't think I know the answer, so you probably have to ask somebody else.
Okay. Google. No, this is not a simple Google.
Okay, I'm trying to think if there's anything else that I needed to tell you. Pretty much the bottom line is that each one of these macroscopic changes relates to microscopic changes, which in turn relate to things like forces and energies, mass, stuff like that at the microscopic level for those gases. So just kind of on your own time when you're looking at the handout, go to this site or similar kinds of things and play around a little bit to get some intuition. Otherwise, that's basically it. I don't know if you guys have any other questions.
What's the site called?
Oh, it's on the handout.
Oh, it's on the handout. Oh, perfect.
Yeah, it's some big long thing. I just searched for like gas applet or something like that. This one came up. There are some other ones with prettier colors and stuff.
You want your